Welcome back to all. So this is the 33rd lecture on quantum mechanics, and in this lecture I will talk about the rotation vibration interaction. Now this is the rotation vibration spectra that I have discussed in my previous lecture. So you can see that in the rotation vibration spectra there are two types of branch. One branch that is called R branch and another branch that is called the P branch. Now the main problem in these types of rotation vibration spectra is that you can see that the separation between the two consecutive lines in the R branch, that is designated as delta omega R, is always less than the separation of the corresponding two lines in the P branch. So you can see that delta WP greater than delta WR. So this is basically in case of perfectly harmonic oscillator model system, these two separation will be same, but if there is any anharmonicity in these types of system, this will result into these types of anomalies or these types of phenomenon. So we will try to understand that why these types of phenomenon is occurred due to the interaction between the rotation and vibration. So I will just again refresh the memory of our harmonic oscillator model system and rigid rotor model system. In case of harmonic oscillator model system, I have told you that the two atoms, they are bonded by some kinds of covalent bond, and this bond is having a spring constant K, and the distance or the internuclear distance between the two atoms is R, and M1 and M2 are the mass of this two atom, and the potential energy of this harmonic oscillator model system is Vx equal to half kx square, where x is basically the deviation from the equilibrium bond position. So at equilibrium bond position, the potential energy is minimum, which is equal to 0, and as these two atoms stretches or compresses, they gain potential energy as x increases or decreases. So this is the expression of the potential energy, and this is the expression of the vibrational frequency. Nu is equal to 1 by 2 pi root over of k by mu, where mu is basically the reduced mass of this system, and the reduced mass of this system is being designated as m1 into m2 by m1 plus m2. Now the expression of energy for this types of harmonic oscillator system is En is equal to h nu n plus half, where n is the vibrational quantum number. Now this energy expression can be expressed in terms of wave number. So the energy expression in terms of wave number will be equal to En hc omega e into n plus half. Omega e bar is equal to 1 by 2 pi c root over of k by mu. So if you just divide this nu by a term that is called wavelength, or sorry, the speed of the light, then the term nu by c is called the omega e bar, and the unit of this omega e bar is basically the unit of wavelength, that is wave number, that is centimeter inverse. So the unit of this omega bar is inverse of the wavelength, and it is called wave number. So this is the harmonic oscillator model system. Now these two atoms can also rotate around some common center, that is called the center of the mass. So this center of the mass situated in between, anywhere in between these two atoms. It is depending upon the mass of these two atoms. If the mass of M1 is higher than the mass of the M2, then the center of the mass will be more inclined towards this atom, the first atom. Now you can see this is the bond distance R1, and V1 and V2 are the velocity vector of these two atoms. So for this system, the moment of inertia is equal to mu into r square. Moment of inertia is nothing but basically a resistance to angular acceleration. So you can compare this moment of inertia with mass also. Now the energy expression for these types of rigid rotor model system is Ej is equal to B bar Hc j into j plus 1, where B bar is called the rotational constant. Okay, so the expression of the B bar is h by 8 pi square c mu r square. So this rigid rotor model system, we assume that the bond distance or the bond length in between the two atoms are not changing. So that's why we called it a rigid rotor model system. So and this is the this omega e bar term, this term is called the vibrational constant, similar to this b bar term, that is called the rotational constant. Now what happened, that if this atom vibrate as well as rotate, both thing happen, in that case the energy expression will be the combination of these two energy. So the energy expression for a model rotation vibration model system is ENJ equal to HC into omega E bar n plus half plus B bar J into J plus 1, where n and j are basically the vibrational and rotational quantum number, and the n and j can be any integer value right from 0 to infinite. Now the selection rule for the transition of these types of vibrational spectrum is delta n is equal to plus 1 and delta j will be plus minus 1. So if delta j is plus 1, then the corresponding lines that is occurring, we called it R branch, and for delta j is equal to minus 1, the corresponding lines that were occur, that is called P branch. And this omega e, that is omega e bar, is called the fundamental vibrational constant that will be situated in between the P branch and R branch. Now you can see that this is the perfect this is harmonic oscillator model. So these are the, you can see these are the vibrational energy states for n is equal to 0, n is equal to 1, n is equal to 2, and in between this vibrational energy state the rotational energy levels are situated. For j is equal to 0, 1, 2, 3, similarly for this level j is equal to 0, 1, 2, 3. Now you can see that the selection rule is delta n is always positive, that is plus 1. Now for delta j is equal to plus 1 occur in between the energy levels, suppose 0 to 1. So you can see that the change of delta j is plus 1, and the wavelength or the wave number of the corresponding transition is expressed as omega r bar is equal to omega e bar plus 2b into j plus 1. So this is the wave number associated with the R branch. So how this wave number came for this types of R branch, I have already discussed in my previous lecture. You can go back to that previous lecture to understood why this equation came. Now similarly, when for P branch the selection rule is delta j is equal to minus 1. So during the transition the j value will decrease. So you can see it start with n is equal to 0, j is equal to plus 1, and it ended up at n is equal to plus 1 and j is equal to 0. So here delta j is equal to minus 1, and the wave number associated for this types of transition is equal to omega p bar is equal to omega e bar minus 2b bar into j. So these are the wave number associated with the lines in P branch. Okay, so you can see that for a perfectly harmonic oscillator, the average R0 that will remain same. Whatever the vibrational quantum number is 0, 1, 2, the average bond length will always be same in case of perfectly harmonic oscillator model system. But we know that the life is not so, actual life is not so simple like a harmonic oscillator model system. In actual case, the potential energy diagram in the two-dimensional will look like this. So you can see that it is not a perfectly parabolic system. The actual potential energy function with distance will look like this. So you can see that in real situation, due to the presence of harmonicity, the average bond length will increase with the increase of the quantum number. So you can see that at these are the average bond length, and the average bond length is increases as this vibrational quantum number increases. So this is basically the effect of anharmonicity. So basically we can see that as the vibrational quantum number goes up, the average bond length is also goes up. So and so the moment of inertia I will also go up, as the equation of the moment of inertia is I is equal to mu into r square. Now the expression of this rotational constant is h by 8 pi square c mu r square. So as the vibrational quantum number goes up, the average bond length is also goes up, which resulted in the decrease of the rotational constant with vibrational quantum number. So you can see that this rotational constant is not actually a constant figure, it is basically a function of the vibrational quantum number. So as this rotational constant is a function of this vibrational quantum number n, here in this equation we can express the dependency of this rotational quantum number with this vibrational quantum number n by this equation, where Bn bar is equal to Be bar minus alpha E bar into n plus half, where B is the potential at the minimum bond length, that is R is equal to Re, or we can say that when the bond length is at equilibrium bond length, or when the potential energy is 0, the bond length corresponding to that state is called the Re. So at R is equal to Re, the corresponding rotational constant is Be. Now alpha E is basically rotation vibrational interaction. So this will serve as decrease the value of the Bn as the vibrational quantum number increases. Okay, so you can see that the value of this alpha is always positive. So this value of this alpha E is always positive. So as this vibrational quantum number increases, as this n increases, the Bn will decrease because it is there is minus sign in this equation. Okay, so using this model we can actually calculate the change in energy in the R branch and the P branch. Okay, so you can see this is the final energy expression for this types of model system, where everything is same except this term B. Instead of B bar we write Bn, because this rotational constant is now the function of this vibrational quantum number. Now we will calculate the change in energy in case of R branch. So delta Er is equal to En plus 1 J plus 1, so the energy associated with n plus 1 and j plus 1 state minus the energy associated with nth state and j state. As we have told you that in case of rotation vibrational spectra, the selection rule is delta n is equal to plus 1, and for R branch delta j will be plus 1. So you can see, so if we just abstract this energy of this two value, we will obtain the final difference of energy in case of R branch is equal to Hc omega E bar plus P bar n plus 1 j plus 1 into j plus 2 minus Bn bar j into j plus 1. Now we can always express this energy difference in terms of the wave number. So this omega bar is can be obtained by dividing this delta E with Hc. So whatever the unit that we will obtain will be in the unit of the centimeter inverse, that is inverse of the wavelength. So that's why it is called the wave number. So in terms of the wave number, the energy associated with R branch will be equal to or we can say the wave number associated with R branch will be equal to this one, omega R bar is equal to omega E bar plus P bar Bn plus 1 bar into j plus 1 into j plus 2 minus Bn bar j into j plus 1. Similarly, we can also determine the energy difference in case of P branch, and from that we can calculate the wave number associated with that P branch, which is equal to omega P bar is equal to omega E bar plus Bn plus 1 bar j into j plus 1 minus Bn bar into j plus 1. Okay, so you can see that this is the rotation vibrational spectra, and these are the R branch and these are the P branch. Now we will just compare the energy gap, that is delta omega R and for R branch and P branch. So for that we have to choose the similar difference between the similar lines. Okay, so if you compare this, then we will calculate the energy gap between the two consecutive lines in R branch is equal to delta omega R bar is equal to omega R at j plus 1 and omega bar R at j. Similarly, the energy gap in between the two consecutive lines in the P branch will be equal to delta omega bar P is equal to omega bar P at j plus 2 minus omega bar P at j plus 1. So you can put all those expression for omega R at j plus 1, omega R at j, similarly for omega P at j plus 2 and omega P at j plus 1, you will obtain the value of this omega bar R and delta omega P, and if we just subtract these two value, you will finally came to this equation. So all those equation I am not going to derive. You can test it in your home, because we are not so much bothered about the mathematics. We are more bothered about what is the outcomes of these types of mathematics. So the difference between the difference of the gap in case of P branch and in case of R branch and are delta omega bar R and delta omega bar P. So if we just subtract them, we will obtain the value is equal to minus 2 into B bar n minus B bar n plus 1. So you can see that this is the equation that we have obtained in my previous slide. Okay, now we have already told you we have defined the equation of this B bar n, that is equal to B bar E minus alpha E bar into n plus half, where alpha E basically rotation vibration interaction term. Okay, and this B bar E is the rotational constant at the equilibrium bond distance. So similarly we can calculate the equation for B bar n plus 1, that will be equal to B bar E minus alpha E bar plus n plus half plus 1, that is n plus 3 by 2. So if we just subtract these two value, B bar n minus B bar n plus 1, we will obtain alpha E bar. So you can see that the difference in gap in between the R branch and P branch is equal to minus 2 alpha E bar. Now as we know that this alpha E bar is always equal to 0, so this difference is always less than 0. So we can say that the delta omega R bar is less than the delta omega P. So from there we can conclude that the spacings in the R branch is less than the spacing in the P branch. So the difference between the delta omega R and delta omega P is directly proportional to this rotation vibration interaction. So you can see that this rotation vibrational interaction is basically a measure of the anharmonicity in the vibrational potential energy surface. So more this value of this rotation vibrational interaction term, more the anharmonicity in the system. So as the vibration gets more anharmonic, alpha E will also increase. So there will be more pronounced difference between the spacing in the lines in between the R branch and P branch. So that's all it from the chapter of rotation vibration interaction. So if you do have any questions regarding this lecture, you can ask me through the comment section. And thank you very much for watching this video, and please subscribe to my channel Chembiosis for these types of lecture based on quantum mechanics. Thank you.